Okay, so let's start from where we end up last time. Quick refreshment. I was doing in last session basically finding k, and that k after which will become unstable. The system becomes unstable, and this is basically we need to find the gain margin and find it in unitless, not in decibel, in unitless, and you get it. So gain margin, you go to minus 180 and find it. Also, we did the same another exercise, also find k, and we found like no value of k will make the system unstable. So all value of k will keep the system stable. There is no k that makes the system unstable. Then, and this basically was in our chapter which we call interpreting Bode diagram. And interpreting Bode diagram is very important for controller design and also for system identification, as we will see later. Okay, so this chapter is really very important. All right, and we started talking about how to draw a Bode diagram. Okay, for this we said we have some standard functions that we need to know how to draw them in order to be able to draw manually using hands a very complex transfer function. We started by g of s equal constant, and this constant could be more than 1 or between 0 and 1, and we found the Bode diagram for it, usually 20 log of the magnitude and the phase of. Then we did for pure integral or integral factor 1 over s, so replaced s by j omega, and we get the magnitude of it, and we found its slope with minus 20 decibel per decade. Also we found the magnitude, and it's independent of the frequency omega, which is equal to minus 90. Also we did for the derivative, so now we need to remember constant is directly when you say a constant, then constant term, then that's how we draw. Pure integral, that's how we draw, minus 20 decibel. Pure derivative is plus 20 decibel per decade. And with, if it's derivative, so the phase lag is plus 90. So 90 degree in advance. So if it is integral, 90 degree behind, lag. Okay, here is 90 degree lead. Alright. Or actually the derivative is a lead. So this is lead and this is lag. Sorry, this is lag, like minus 90 degree behind. Integral is lag. So looking to the past, derivative is lead, so 90 degree lead. So in advance phase. A slope 20 decibel per decade. So what if it is a first order system like 1 over ts plus 1? This will be, as we demonstrated, we have two asymptotes with the corner frequency equal 1 over t. 1 over t is the corner frequency. So then this, you could write it this way. 1 over, so 1 over omega s plus 1, because t is 1 over omega equal 1 over t, and this omega is the cut-off frequency or the corner frequency or the break frequency of your filter of your first order system. Okay, that's how it looks like, and we draw it by following the demonstration. We have two asymptotes here and here in the red zone, and the error here is -3, approximately -3 decibel. So we said like approximately you could take the two asymptotes together, and where they meet is the corner frequency, which you can know directly from here. So it is 1 over omega. Let's say, so t equal 1 over omega, omega equal 1 over t. Yeah, this is the cutoff frequency. And the phase 0 to -90 for first order system, and at the cutoff frequency or corner frequency you have minus 40 degree, minus 45 degree. So now let's draw for first order factor. So see, now it's not like 1 over ts plus 1, it's basically ts plus 1. So derivative term, I expect to have now a slope of plus 20 decibel per decade. Not like this. Here is minus 20 decibel per decade. So I expect in the derivative term ts plus 1 or first order factor to have plus 20 decibel per decade and to have positive phase. Let's do it together and check if that's it. So first, as we doing always, we need to check the magnitude, and this is the magnitude. Magnitude we call it decibel. (20 log 10 of tj omega plus 1, which is equal 20 log 10 of that magnitude, which is 1 plus t omega square. At low frequency, this is equivalent to when frequency is low, 20 log of 1, 0. At high frequency, so this is equivalent to t omega square, so t omega, so 20 log of t omega. And as we always doing, in this case, take the case when omega equal 1 over t and find it. So at low frequency, let me assume we have 0. Alright, so as maybe I put it in red. Low frequency, I have asymptote at 0. This is the asymptote. And at high frequency, I have another asymptote which is equal approximately 20 log t omega. Let's see, at 1 over t, it's 0. At 10 over t, so if 10 over t, 10 log, so 20. 10 over t, approximately, this is 20. So you have a line, as we said, logarithmic, we're taking them all line. So at infinity, I'll be having asymptote. So how it behaves exactly? It behaves this way. So it is coincident with the asymptote at 0 at low frequency and high frequency, and here it's not. So maybe I draw the asymptote in red. And where is the cross the asymptote? The two asymptotes, this is at 1 over t, which we call it again the corner or break frequency. Corner or break, so break EA, break EA, break frequency. Yeah, basically that's it. And the error here is, as we said previously, is around 3 decibel, as we said in the integral factor. You could draw only the asymptote this way. You see how it's different from the case of first order system, 0 minus 20, here 0, 20 decibel per decade. So this is 20 decibel per decade. So this is 1 over T10, 1 over T10 etc. 1 over t100, so decade. Then the scale is a little bit different from here, but so now for the magnitude. This is for the magnitude. Now for the angle phase. So the phase equal the phase of t j omega plus 1, which is tangent minus 1 of imaginary over real. Tangent minus 1 of t omega. Again, at low frequency, I have a tangent minus 1 of 0. So phi approximately equals 0. Tangent minus 1, 0. At high frequency, phi equal tangent minus 1 of infinity, and this is 90 degree. At corner frequency, which is phi equal, so not approximately, tangent minus 1 of 1, and this will be 45 degree. Therefore you have 90 asymptote of 0, and asymptote of 90 at infinity, and in between at 1 over t is 45 degree. So then yours will be something like that. Okay, maybe if you want to have the two asymptotes together, they look like this. Very nice. We was talking last time a little bit briefly about the Bode diagram of a second order system. Alright, and we said we have three cases: zeta bigger than 1 or zeta equal 1. So in this case you have it is the summation of, or the product of, second order system could be written as the product of two first order systems. So we don't need to study, we only study the case where zeta between 0 and 1. And if zeta between 0 and 1 we found will be 0 at low frequency asymptote, and at high frequency I have minus 40 decibel per decade. So now it's second order system. My system is not anymore minus 20 decibel per decade or plus 20 decibel per decade if I have derivative. So here it is minus, not 20, minus 40. So if it is third order system, you could expect to have minus 60 decibel per decade, and so on. So now it's second order, so I have an asymptote at minus 40, as we demonstrated last time. And the phase 0 not to minus 90 as a integral factor. So it is 0 to minus 180. So if you have minus 60 decibel per decade, you should expect a phase up to minus 270 degree. So here because your slope is minus 40 decibel per decade, so your phase, you could know it is minus 180. As we demonstrated last time, it was minus 180. And therefore at the corner frequency, here the corner frequency is omega n, is your natural frequency, because at this frequency you have a peak amplitude, and as you can see, if excited at an input equal to omega n, equal to the natural frequency of the system itself, so I could expect peak if my zeta between 0 and 1. Alright, and that's what we saw. So when I vary zeta, the peak will vary. If you decrease zeta, so then your peak amplitude will increase and becomes very close to the asymptote in the angles. That's what we saw, and they are here in your slide. Okay, so you are here. So as we said, if it is zeta so if zeta more than 1, it's overdamped, and therefore G is a product of two first order systems. So now what is the magnitude? So we calculate the magnitude when zeta between 0 and 1 at low frequency, at high frequency, and we get the asymptote as we demonstrated last time. So now when zeta between 0 and 1, also we could find the phase, and that's the phase at low frequency, at high frequency, at the corner frequency, as we always do. At low frequency, tangent minus 1 of 0 is 0. At high frequency, tangent minus 1, so look at it, omega equal infinity, so this is also 0. So then tangent of 0 is 0, but could also be pi. It also could be 2 pi, 3 pi, 4 pi, etc. So then, because here it was at low frequency was 0, and I know it's going to go down, so then this is, we take the first one, which is pi. So then, because I have minus, becomes minus pi. So then 0, it goes to minus pi at infinity. At corner frequency, tangent minus 1 of infinity, it's 90 degree. So at 90 degree, at pi over 2, I have infinity, as we saw in previous session, so minus 90 degree. Alright, that's what we demonstrated, and look at when zeta is between 0 and 1, how the peak will change. And this peak, we could calculate it. And this is also very important for system identification. If you want to identify, if we find a system looks like this, has asymptote at minus 40 decibel per decade. Like here, for example, it has an asymptote at minus 40 decibel per decade, and it has a peak this way. So you need to find the system, and we know it's a second order system. So how to find it? By looking to the magnitude, for example. How can I find zeta? You can find it by this peak. And how to find omega n? Two things. If you find, then you find the system, zeta and omega n. Omega n, so it's where you have the peak. So this is your omega n. So easy to find omega n, but zeta, how to find it? Okay. Let's study to find it. Let's find the maximum j omega magnitude. How much this maximum is? Well, this maximum of magnitude occurs when the magnitude of the denominator is minimum. That's the magnitude of the denominator. Right? It's a complex number, magnitude of it. You get real plus imaginary, real square plus imaginary square. So this is, if it's minimum, I get the maximum. If this is minimum, I find the derivative of it equals 0, so I can find the omega at which I have this minimum. Therefore, I have maximum amplitude. And this omega is, we call it the resonant frequency. So now we can see exactly the resonant frequency is not exactly the natural frequency. The resonant frequency is not equal to omega n. Natural frequency equal to omega n if you have no damping ratio, if your damping is 0. So that's only in this case. So this is more general than. If you neglect the damping effect, then you can say the resonant frequency equal to the natural frequency. But if it's not the case, it's close to it. That's why most of the time we consider it same resonant frequency equal to natural frequency. Actually, and you experience this if you get the chance later to work on some damping system, you experience is not exactly the same. It's close to the natural frequency, but it's not. Even you can do zoom here and see exactly the peak where it is. For example, at 0.1, if you have 0.05, maybe you can closely find it. and so on. So you see the peak is not like, for example, look at here at 0.5. The peak is not exactly at omega n. So it's changed to be close to omega n, depends on zeta. When zeta equals 0, if you keep decrease up to 0, so then you get exactly equal omega n, omega f. So it's resonant frequency. For example, here when zeta equals 0.5, it is lower than omega n. The peak, clearly we can see it. So then the resonant frequency on which you have maximum amplitude is omega r. So now I put omega r in here exactly in the magnitude of jg omega, of gj omega, in order to get how much is the amplitude in decibel or not in decibel. So if you don't want it in decibel, just put omega r in omega and find the magnitude. You get jg omega maximum equal to 1/2 zeta square root 1 minus zeta square. And this formula is very important in finding zeta, because if you know, if I give you the graph and you know the amplitude, how much it is, how much this is, you can measure it on the graph, so you can find zeta then. That's how to find zeta. But pay attention here, you have it in decibel. So then the value that you find in decibel. So you can find then the resonant peak without unitless. Okay, so here you have two cases. When zeta bigger than 0.7, somehow you start have no resonant peak. You don't have resonant peak according to some calculation. When you do the derivative, you find depends in zeta you have or you don't have resonant peak. So when zeta more than 0.7, we are very close to zeta equal 1 or a critically damped or overdamped system, so you have no resonant peak in this case. So that's why here, if you wish, in this table they put distinguish between when you have zeta between 0.07 or above 0.7. If you have above 0.7, you have no resonant frequency, or you have no resonant frequency, but the magnitude, maximum magnitude, is equal to 1. Of course, maximum magnitude, it is here at low frequency. For example, let's take the case when zeta equal 1, for example, or zeta equal maybe 0.7, or maybe let's say 1 is more, because 0.7 is like included in here. Even so, it's very small. So look at when zeta equal 1, the maximum magnitude is here at low frequency. After it, the magnitude is smaller than 0 decibel. So 0 decibel, it's 1 with unitless. And resonant frequency, no resonant frequency. Magnitude, maximum magnitude is 1. Otherwise, between 0 and 0.7, this is the formula that you apply for the resonant frequency and the magnitude of the peak. Good. And again, this is very important for system identification to find the zeta. All right. So last time we tried to solve this together. Basically, this is very important, because that's how you draw the complex. Here they are telling you the general procedure to draw a complex Bode diagram. First, you need to write your transfer function in the general form. So just I give you on the exam, for example, this transfer function, g of s equal 10 s plus 3 over s plus 2 s2 plus s plus 2. Okay, you need to draw the Bode diagram for it by hand. You see, it's complex, but we know how to draw for constant, how we draw for a derivative, for an integral factor, and for second order system. And then at the end, it's logarithmic, so the product of them is the addition of the graph altogether. for phase and for magnitude. So we do adding. So then the only thing we need to do is to convert this to small standard form. And as I told you, the standard form, you need to remember them by heart. So those are what we study up to now are the standard form. So we need to remember them by heart, like S, 1 over S, integral factor, derivative, first order factor, derivative, second order system, etc. So as we did last time, so what's the standard form of S plus 3? Always we have 1. You remember in the standard form we have 1. So then S over 3, so this is will be, we did it last time here, so let me do it again. 10, so S over 3 plus 1. And you have 3 common. So S over 3, we know this is a derivative factor with directly with a cut-off frequency or corner frequency equals 3. Then S is pure integral. We know how to draw it here, so we need to take 2 comma and S plus S over 2 plus 1. So we know 1 over S plus 2 plus 1 how to draw it. Then in here also we need to take the 1 common, so S2 over 2, so here times 2 then, plus S over 2 plus 1. And this is a second order system, we know how to draw it. By adding all together, and doing it this way, so here 30 over 4, you get 7.5. Then just the remaining part. So we have two things you need to remember: body form and corner frequency. And those are the body form. This is the standard form we know. This is standard form we know, etc. So you can draw. And the corner frequency here, omega equals 3, omega equal 2, omega equal square root of 2 according to the standard form. So if that's the case, so now you can draw the body diagram. As a direct application, I go with you on this exercise. So in this exercise, we're asking you to draw the body diagram, so the magnitude and phase for this system. Alright, so how to start? You need to convert it to the basic form, and this is the first step. So G of S equal to 2000, then times 0.5, then let me write times this way, S over 0.5 plus 1, then S times 10, S over 10 plus 1, times 50, S over 50 plus 1. So that's the general form. Based on this, if I ask you how to continue from there, so 10 times 50 is 500. 500 times 2, then 1000. 2000 over 1000 is 2. So 2 S 0.5 plus 1. So this is the standard form then. S over 10 plus 1 and S over 50 plus 1. Now you are in the standard form. So then this is the first step you need to do. And replace S by J omega. S is J omega. Don't forget. So then second step you need to do is to find the body form. What are the body form? Standard form in which you can start drawing your body diagram. 2 is a constant. S over 0.5 plus 1. So you know how to draw the constant. You know how to draw this. This is a derivative factor. So 0, 20 decibel per decade, corner frequency 0.5. Very easy. So then 1 over S. This is standard form. I know how to draw it. This is minus 20 decibel per decade and phase minus 90. So you need to remember them by heart, the standard form, how to draw them. So quickly you can draw everything. So then 1 over S over 10 plus 1. This is a first order system with 10 corner frequency equal to 10, and yeah, basically 0 to minus 90 degree. So two asymptote 0 and minus 20 decibel per decade, corner frequency is at 10. So you draw it. Of course, S equal J omega, don't forget. And 1 over S over 50 plus 1, exactly same as this, but corner frequency is different. By this, I draw all of them and I add them together. So what are the corner frequencies? Step 2, continue on step 2. Corner frequencies. So for here you have 0.5, for here you have 10, and for here you have 50. So omega, of course. So once you're done with this, so now let's draw the body diagram. 1, 2, 3, 4. I draw 5 body diagram, phase and magnitude, and I add them all together. So let's draw the 5 body diagram. 1, 2, 3, 4, 5 body diagram for this 5 systems separately, then later on add them. So then 1, 2, 3, 4, 5. Let's start by 1. It's a constant. So remember, for the constant, it's 2. So then you should have here 20 log of 2. 20 log of 2. And phase of 2 is 0. So that's the easy phase diagram. Then S over 0 plus 5 plus 1. Let's assume this is the 0.5. Alright, here is the 0.5 frequency. So then this is the corner frequency. It is first asymptote 0. At the corner frequency it will go 20 decibel per decade. So 20 decibel per decade. So then I go like this. And this is 20 decibel per decade. So just I will note it here, 20 decibel per decade. That's simply what you do. 0, of course you have the real one, but we don't care about, just we do the asymptote 0, and minus second asymptote is minus 20 decibel per decade at 0.5 corner frequency. Then phase is 0 at 0.5. we are considering plus 90. So plus 90. Alright, 0.90. Maybe I draw it better. Just that's how it look like. If you wish the exact one here and there, you know, like at the corner frequency we have, and then we meet it later on. And here is the corner frequency, that's the one. Okay, so if you want to draw the exact one, again I don't want to draw the exact curve. So 0, and I go line of minus 20 decibel, 20 decibel per decade. This is graph 2. 0.90. If you want here 0.45, etc. So here is the 45. So 1 over S. Let's draw 1 over S, which is number 3. Number 3, if you remember it, this is standard 1 over S. It is at 1. So let me consider this is as 1 radian per second. At 1 is 0. Otherwise it is minus 20 decibel. So it's enough a point and a slope to draw the line. At 1 it is 0, if you remember, the 1 over the pure integrator, so it's a standard form, and otherwise it is minus 20 decibel per decade. In case you don't remember, you return directly to your course, and you look at 1 it is 0, otherwise minus 20 decibel. So then minus 20 decibel per decade. So maybe here I'm not really considering, but the slope, just I write on it minus 20 decibel per decade. So minus 20 decibel per decade. And what about the phase? The phase is minus 90 degree. It is, okay, I'll put it like this, it's minus 90 degree. So here is the phase. Alright, let's look to phase diagram 4 and 5 later on, add all together. So the 4, 1 over s over 10 plus 1, and this is what? This is an integral first order system. So if it's an integral first order system, then let me assume this is the 10 decibel, 10 radian per second. Alright, and later for this one, which is factor 5, the component 5, if you wish, standard function 5, is also has 50 radian per second. So 10 and 50, and both the same, just the corner frequencies. So I take this as 10 and this is as 50. Alright, so if that's the case, even if it's not on scale is alright, as long as you know you are putting it, this is 10, this is 50, so you know in your scale. Better if it's consistent somehow. So then I have two Bode diagram, one first order system, so I know it's 0 everywhere. When you reach the 10, so you need to go minus 20 decibel per decade. So then you go minus 20 decibel per decade. Okay? So minus 20 decibel per decade, and so this is the 10. And for the phase, 0 minus 90. 0, if that's a 10, we are 0, then minus 90. Of course, if you want the exact one, is 0, here 45, then you go to minus 90. And for this one, it is this way. You keep, alright, so you need to keep up to here is the 50, then you go minus 20 decibel per decade as well. Minus 20 decibel per decade, right? We draw the asymptote correctly, it is 0. Alright, basically that's it, and here it is 0 degree, and then minus 20, minus 90, minus 90. If you want the exact one, is 0, minus 45. Alright, so now you add all the 5 together to get the Bode diagram, and you add all the phase together to get the phase. And basically that's how we draw the phase. So now we will add them all together. Good. So now what you need to do is to add all of them together. So let's start by the magnitude and adding all of them together. So starting at low frequency, you have 20 log of 2, 20 log of 2 plus 0. So basically from 1 you have 20 log of 2. Let me write it here. At low frequency, from 1 you have 20 log of 2. From 2 you have 0. From 3, so from 3 you have AB, so here 20 log of 0.5 if I'm taking it here at this point, 20 log of 0.5. So here 20 log of 2 is a point 0, 20 log of 0.5 plus 20 log of 0.5. Of course, taking everything is magnitude, right? So absolute value. Anyway, if it's negative, so we take the absolute value because I'm adding them. From 4 it is 0, and from 5 it is 0. Then this will give you a 20 log of, if you do the summation, you find 20 log of 4. Yeah, look at it. You will do the derivation. Here is 0.5 means 1 over 2. So 20 log of 1 minus 20 log of 2 minus 20 log of 2. Absolute value of it is 20 log of 2. So 20 log of 2 plus 20 log of 2, it's 20 log of 4. And then you can compute how much it is. So then at 0.5 I have 20 log of 4. So 20 log of 4 and minus, because that's here the separation point, so I'm interested to look, and I go minus 20 decibel per decade this way. Then assuming this is minus 20 log of 4, this is the 20 log of 4, assuming here is the 20 log of 4 at 0.5, and then otherwise it is minus 20 decibel per decade. Okay, so this is at 0.5. What will happen after it, after this one? Like, look, if you look to the all the Bode diagram, here is constant, and here it is, look very well, it is plus 20 decibel per decade, and here it is after 0.5 minus 20 decibel per decade. So this will cancel each other. So look at it, plus 20 and minus 20, so they're canceling each other up to here, up to 10. So up to 10, then you have constant. So you keep constant up to 10 radian per second. Then up to, this is the 1, this is the 1, this is the 0.5, this is the 10. Up to 10, you are constant, because the minus 20 decibel and the plus 10 decibel and minus 10 decibel, they cancel each other. And then you add up to 10, and then in here you have minus 20. So then you go minus 20 up to 50, and another minus 20 at 50 radian per second. So then from 10 to 50 you have minus 20, and from 50 toward infinity it becomes minus 20 plus minus 20 is minus 40 decibel per decade. So then you have minus 20 decibel per decade, so you put the slope of minus 20, and then minus 40 decibel per decade. But the question is at 50, so then the question is, if that's minus 20 decibel per decade and this is minus 40 decibel per decade, I may ask the question, who said this will be here at this point? Maybe minus 20 decibel, it goes from here up to here, maybe at 50 it is here, minus 20, that's the slope. Who said that's the slope of minus 20? Are you sure that's minus 20 decibel per decade? The blue one or the red one, or maybe the green one? Alright, so then what I want to know, at 50 radian per second, where is the slope, where it ends up? Which one is the correct? So then I will compute from here what's happening at 50 decibel per decade. So let's see what will happen at 50 decibel per decade. I'm in blue. So at 50 you have 20 log of 2. 20 log of 2. It's positive. I know it's positive. If it is between 0 and 1, so I take the absolute value. What's happening here? It's 20 decibel per decade. So if it's 20 decibel per decade, then here, how much is from here to here? Maybe I put in green. So this magnitude, how much it is? This magnitude, how much? So 0.5. Look at it, 0.5. Per decade, it is 0. Per decade, so at 5, here maybe the 5, it's 20. At 5, it's 20. Another decade, 50. You should add more 20, so then it becomes 40 decibel. So then plus 40 decibel plus how much is from here to here in decibel. At 1 you have 0. At 10 you should have minus 20. At 100 you should have minus 40. So at 50 should be minus 30, right? Because here minus 20. Per decade is minus 20. So half decade, so then minus 30. So minus 20 at, because here is 1, here is decade, so it becomes minus 20. If that's the other decade, you have minus 40. So at 50, you should have minus 30. Then here is minus 30. Here at 50, minus, so you could now tell me yourself how much this will be. This is 10, and this is 50. So at 100, you will get minus 20. Because decade, because it was 0 at 10. So at 100, you will get minus 20. So at 50 minus 10, then it is minus 10. Alright, so minus 10, and here plus 0, plus 0. So you end up having 40 minus 40, 0, 20 log of 2. So then at 50 you have 20 log of 2. Alright, so at 50, 20 log of 2. Then no one of them is correct. 20 log of 2, if this 20 log of 4, so 20 log of 2 somehow here. Okay, then it should be here. Here is the correct one. So now you're able to understand how to go. Alright. So then it will go like this. This is the minus 20 decibel per decade, and this is the minus 40 decibel per decade. So now you draw the phase. So also you need to go add them. Phase is adding them very easy, because minus 90, 90, 45, etc. And also even easiest way, you could check it yourself. If it is minus 90, minus 20, directly it reflects a phase of minus 90. So then it is minus 90. If it is constant, it reflects a phase of 0. Okay. If it is minus 20, so it reflects a phase of minus 90. If it is minus 40, so it will be minus 180. Okay, so now minus 180, and this is a phase diagram, and this is Bode diagram. Of course, if you want the exact one, you can go asymptote here 3 decibel, then in here close to, then here like this, in here maybe here minus 3 decibel, then asymptote. So you don't need the exact one, but here the exact one is easy to draw it actually, just because we know we go this way and then maybe this way. Okay, that's how it look like, and that's everything about Bode diagram, how to draw this. I think here we did very complex transfer function, and you were able to draw it by decomposing it. So now any transfer function you can decompose it into standard form and adding all the 5 together if they are 5, and then you get the final form. That's the same methodology. You need the same steps you need to use each time you ask to draw by hand the Bode diagram, or if you don't. But this is very important to know how to draw by hand because it helps in system identification. We told you on root locus you need to understand it, but really maybe using MATLAB is alright. You don't need. Even so, I asked you to draw an approximation way by hand. Here, this is important to extract the system identification, to be able to identify a system by looking at the Bode diagram itself.